Good morning, everyone. Let me introduce ourselves for a start. So I'm Jamet. He's Thiago Alves. We are software engineers at J-Architects, which is based in Belgium. And we are here to talk about machine learning and bees today. It's a bit different of normal track, I assume.
All right. But before starting, I would like to say that this project was developed as my master thesis last year, and that I'm very glad for my advisors, for everyone that helped me during this process, and also the universities, both universities that contributed with this solution. But back to the bees. As this is a machine learning conference, probably you don't have a background on beekeeping, so I will give a brief introduction about the beekeeping process, even if I'm not a beekeeper. Before starting going with more depth to the machine learning part. So what you are seeing here is two beekeepers. They are working on a bee colony, and this is in boxes like this that most of the domesticated bees lives nowadays. And inside of these boxes, you can find frames like these. And in these frames, you have a structure made with a lot of cells, and these cells are created by the bees. Inside of these cells, you can have a lot of different contents, but most of the contents can be separated in two categories. The first one is the brood, with the different stages that the bee have before becoming a adult bee. These stages are the egg phase, larva phase, and the capped cell. We also have another class, another group that is the food reserves, and in this group we can find the honey, nectar, and pollen. We also have some different kinds of cells, but they are not so significant for our purposes. And also we have the empty cells. We define the cells in this project as the name of this class as other. And looking at these classes, it's easier to think that one way to measure how healthy a colony is by counting the number of cells that you have in a set of frames, counting the number of cells with brood and food reserves. And based on that, you can measure how healthy a colony is and measure the strength. And this is the way that most of the beekeepers do this process nowadays. They count it manually. And are two examples that how they make this counting. In this first example, they use a plastic sheet in front of the comb, and they use a marker to make some labels. And after that, they use this plastic across the comb in different epochs of the year to track the development. And in this other example that's easier to see on the field is called the Lieberfeld method, and where they use a kind of grid in front of the comb, and they visually estimate the number of cells of each one of the classes. And as you can imagine, these both tasks are very time-consuming and tedious. But there are more drawbacks. For example, if the beekeeper is not prepared, he cannot count the number of cells fast. So he needs to be trained a lot before doing this task. So it's also difficult to transfer this knowledge for new beekeepers. Because it needs to be fast, there are some problems with the bees itself. Because if the beekeeper is not fast enough, some bees can die during the process because of the stress when he opens the box. So thinking about this problem, we proposed a solution that was to use machine learning and image processing to make this task completely automatic. And this is the final result. And as you can see, the software is able to detect the cells classify them, and in the end count the number of each one of the classes. Okay, Jean, could you tell us a brief pipeline of this presentation and how we get this result?
Well, I can try at least, right? So as everybody knows, machine learning is not that simple. There are many, many small tasks, but to save you the time and the gory details, we split it in 4 big blocks that you can focus and try to understand how we actually end up on that last solution you just saw. So we have data collection step, of course, pre-processing, the cell detection, which is for the image processing part, and then finally the classification to those 7 different classes, right? Well, where did we get the data? We could be using any search engine, for example, Google or Bing or whatever, to try to find a big set of images with Honeycomb, and then try to play around and classify it, right? But this is a very specific domain. It's very hard to find this kind of images. So we couldn't use this approach. We had to actually create our own data set. So for that, in the image acquisition, we actually have the help of, again, the beekeepers and the researchers on the universities. And we came up with a wooden tunnel where we could be able to control the luminosity and the distance where every picture would be taken. And also, we used a professional camera to avoid low-quality images, because, of course, we need to see the details inside of each cell in the comb. So if we use a very simple camera to train, we don't have enough details there. Using this setup, we collect more than 2,000 images, and you have some examples over there and how it's the final result of this first step. So this process took around 3 months?
Yes, 3 months.
To collect all this data. Of course, to create this, this wooden tunnel and so on. And then with this data at hand came the first big challenge, which is actually now how do you select every single cell or detect every single cell in all these frames that we took. It was a challenge because in the team we didn't have experience with image processing previously, but more important, we can see here that there are very different types of cells. And the difference in contrast in such areas, they also make it very difficult to find a general algorithm that would be able to detect everything. So if we highlight those 2 areas, we have the honey area on top, which is some parts is even difficult for us to identify the borders between the cells, while in the lower part we have uncapped cells, which the border are more clearly seen. And this basically imposes us with, can I use any simple transformation or filter that can actually highlight this? We didn't know it. So maybe this was the challenges to find an algorithm that we could apply to this problem. So I hope Thiago can elaborate a little bit more.
Okay. So to find this algorithm that was able to detect the cells across all the different classes, we developed a lot of different methods, and we tried them. Some of them we had good results, but some of them we don't. The first method we tried was the watershed transform, and using this method we tried to make the segmentation of each one of the cells. In the second method that we tried to use, we create some kind of markers in the frame, and each one of the markers have 7 points, and with these points we try to make some horizontal and vertical lines. And we expected that in the crossing areas of these lines we could predict the neighbor cells. But this method didn't work at the first time, because we saw that as far as the cell was from the central marker, the quality of the detection decreased a lot. So after that, we tried another method, and in some way we tried to enforce that each one of the neighbor cells would be predicted by its closest marker.
Well,
this solution.
It's kind of clever, right? To simplify a little bit, but did it solve us? It's done, this step, I think.
No, it also didn't solve the problem, because because 2 main problems. The first one was the lens distortion. When you take a picture, there are some kind of distortion that's caused by the lens of the camera, and this made that even the cells close to the markers was a bit disaligned to the markers, and we couldn't detect them. Another problem that we had was with the creation of these markers itself, because if all the 7 cells are not very aligned, we could not to create these lines and predict the neighbor cells. So even some misalignment on these 7 points could give us a lot of bad results. So yeah.
So in this step we have 3 methods, and you are saying that the second and the 2 didn't work. You give us the reason, but how about the first? Did it work, or?
The first method also didn't work, but it's more related with this area that is one area with honey. And as you can see, the watershed transform was able to make the segmentation of most of the cells, but the area with honey, this method was not able to make the segmentation of areas that corresponds to cells. So
basically none of those 3 methods worked.
No.
How did you solve it then?
We had to develop a 4th method, and in this 4th method we have 2 main steps. The first step is to make the pre-processing to try to enhance the borders of the cells. And in the second phase of this method, we try to make the detection of all of the cells. So this method this pipeline works this way. First we have the input image, the original image, and after we need to make some enhancement. And after some tests, we saw that extracting only the red channel of the image, it gave us a good result related to the contrast. But we tried to improve it even more, the contrast of this image. So we use a method called Clare. This method was very interesting for us because, as you can see, in this image, it's a frame that's still being created by the bees. And as you can see, the bees starts from the center and go to the borders. And this makes that the center of the image is darker than the borders. So when we try to make an equalization to improve the contrast of the image, dealing with the entire image, we have this problem, is that the center gets even darker. So we try to find some way to improve the contrast, but still dealing with this problem, this problem when the bees are starting the frame. So that's why we came up with the solution that was use the Clare method, because this method is able to improve the quality of the contrast and working with small tiles at each time. And as you can see, using the Clare method, we were able to improve the quality of the contrast and still have a good result here in the darker area. So it doesn't get darker. But there's a problem. When we improve the contrast, when you increase the contrast of one image, the noise also increases. So we need to remove the noise after improving the contrast. For that, we used a filter called bilateral. It's interesting, this filter, because while it removes the noise of the image, it still keeps the image sharp. So it preserves the cell's borders. And it was very important for us to preserve the borders for the next step, that is the detection. And for example, if we use a Gaussian filter or average filter, the borders probably we would get lost the borders of the cells. And after all this pre-processing part, we applied a method called circle Huff transform to make the detection of all of the cells.
Okay, so now you have a solution for the detection based on the circle Huff transform. But are we able to detect those low contrast area, those so different, like the honey area and the comb?
Yes, it is, but there's a trick, because this method have some parameters, and one of the parameters decides if there is or there isn't a circle in some region. So if we reduce the threshold of this parameter near to the lower boundary, it starts making some detections even in areas that it's harder to see that there is some cell there. So in this way, we were able to make the detections even in areas that we cannot see the cells there. For example, the honey area. Here we have some more examples. For example, here in the center, we have an area entirely filled with cupped cells, cupped brood. On the top, we have one area with honey, and we also have some uncapped cells. But what was more interesting for us was that this method didn't work just on image of our data set. It also worked with some image that we collected on the internet, and also some images that were taken without a controlled environment or using a smartphone camera, for example. These are some examples.
Okay, but if you pay attention, this image over here, well, this rough circle transform is really good because even the tarmac is detected as cell. So it's not only the comb, but also everything outside of the background now becomes a cell. It's, I don't know if it's that good.
Yes, these results are not so good. We are able to detect the cells, but this method detects a lot of things that are not cells. So that's why we have a special section just for the false positive removal. And in the same way that we needed a lot of different methods and experimentation to find one method to detect the cells, we also need to try a lot to find a false positive method, removal method. Here we will show some examples of the approaches we tried. In the first method, we used again a Huff transform, but at this time to detect lines. We tried to detect the borders of the frame, and in some way to remove all the cells that were detected outside of this inner rectangle. As you can see, most of these blue cells would be detected as false detections and would be removed. But there was still a problem. These cells detected between the comb area and the line and the detected line. So there was space for further improvement. So this is what we did in our second approach. This second approach was the first one that we used as CNNs, and we tried to some way classify each one of the cells as being either real or not. If it is a prediction on the background or on the comb area. So for that, we trained a Google and Net architecture just for making this classification. And as a result, we had a good quality on the classifications, but there was two main drawbacks related with the time. The first one was, if we wanted to use this architecture to make the classification, first we would need to use the CNN to classify, and after we would need to use again to decide which was the correct label of the cells. First we remove the false detections, after we would use again the Google and Net to classify the cells. So we would need to use twice a neural network, and it would cost us a lot of time. And another problem that related to time is that as the image size increases, the time to detect the cells increases more than linearly. So detecting the cells on the entire image costs a lot of more time than detecting only the cells over the comb area. So finding a method to be able to detect only the cells over the comb area would be the best solution for us, because it would save us a lot of time. So this was our third approach. We tried to some way make the segmentation of the comb and make detections only over the comb area. So how did we find? This image is one example of the results that we have, and how we came up with the solution And how we achieve this result? Maybe you are asking yourself. Well, this solution came for me and my advisor when we were working in this Kaggle competition, where the problem was you have one image like this, and you need to make the segmentation of some cells. And across the many different kernels that there was in that the community provided in this competition, there was one that was using a neural network architecture called UNet. So when we saw this solution, we thought, well, maybe this can also work for us. So that's what we tried to do. We had this architecture called UNet, and as an input, we had some tiles of the entire image, and we expected that as output, this neural network would predict a mask showing where the comb was, and where, in which region of the image was the background. And for this training, we need to use to annotate a data set. For that, we used a tool like Photoshop just to paint as white the comb area, and the rest remained as black. So this is one example of our data set. And after using a Python script, we create some tiles of these images, and we were able to create our data set based on these tiles. It's interesting, this neural network architecture, because it classifies the pixel-wise the output. So it's very interesting, this architecture. Okay, and after training, in reassembling the image, these are two results that we found. It's very interesting. As you can see, this object in front of the comb was classified as not a comb area, and these are two results that we got when we processed images from our main data set.
So the images are very well defined in terms of that setup.
Yes.
And if you apply this to another image that you take with a smartphone, for example, or from Google, how would it behave?
Well, it should work, but as most of the machine learning models that are created, they work very well in a specific test that it was trained. We tried to apply this model for images that were taken without using our controlled environment. These, for examples of pictures, they were collected using a smartphone camera, and it was in front of the sun, and the conditions were not so good. And these were the results that we achieved using the same model. As you can see here in this first image, we have some areas inside of the comb area that was segmented as background, and vice versa. You also have this problem, for example, in here. And we could improve this result even more, labeling more images, such as these images that were not taken using our environment. But we had another idea. Using the OpenCV library, we were able to use a method called find contours, and with this method we are able to extract all the polygons of the image. So we extract this polygon, a lot of polygons, and after finding the largest one that most of the time correspond to the comb area, we are able to extract it and print this polygon in a new image completely filled. And in this way, we can remove the false segmentations in and outside of the comb area. So this how we dealt with some images outside of our data set. We could improve it even more, but only training with more data. It's also interesting that using this method, we are able to make the segmentation before the detection phase. So we can reduce a lot the image size before making the detection of the cells. And this increases a lot, speed up a lot the processing, the detection processing. Okay, maybe I talked too much. If you are lost during this process, here we have a checkpoint. Can you explain, Jean, where are we now?
Yeah, let's see the next slide. Well, remember the pipeline we talked about, the data collection and so on, all these phases. So now we have a first step to be able to detect the cells, which is the segmentation process. So instead of trying to detect the cells in the whole image, we segment only the comb area to gain performance, for example, and also to avoid detecting the tarmac as cells, of course. And then we have a pre-processing task, and then the detection algorithm to actually be able to identify where the cells are. And then the next step, of course, since we already detected the cells, is how do we label each individual cell, which is the last task for the cell classification. So just to remember, we have 7 classes to try to tag every single cell. But we need to create a data set to train our models on. So the idea, there was a tool, or we created a tool where the expert could label every single cell, or a few cells, on the comb to create this training and validation test. So basically, in general, for every frame, there was about 20 cells which were labeled manually by the expert, which generates more than 70,000 cells or annotations for the training and validation set. As for the test set, we select a much smaller a number of images, but then with the tool we annotated every single cell, which then generates about 40,000, almost 40,000 annotations to train the models and to be used on a test set. Then the big question is, now we have these images all annotated, the comb area selected and so on, but how we actually input this image to the neural network? How big has to be this input for the neural network? If we choose the big image, the full size of the image, it's going to be training for a while, and we have to wait too much, and so on. The performance is not that good. So we didn't have really a guideline to follow. What we decided is to start from, for example, 40 by 40 pixels, where there is only the cell itself and the label, and we increase a little bit this tiles, giving a little bit more of context about the comb, up to 500 by 500. And then we trained it based on these 16 variations. We trained 16 Inception V3 models and checked some results. We noticed that varying from 40 up to 300, the performance was always increasing in terms of quality of prediction. But also we noticed that the performance and the time of processing, of course, increases non-linearly. So the bigger the image, the more time you have to wait. Taking this information into consideration, also the fact that some architectures, they have some constraints in terms of the input size, we chose 224 pixels by 224 as our input size for the neural network. And then how we actually select the architectures, there was a lot of experimentation, which Thiago is going to describe to you.
Okay. After we deciding which would be the input size, we needed to find the neural network architecture to work with these annotated cells. So we selected 11 different models. All these neural network architectures are well known in the literature, because the good results and image classification competitions. So because of that, we choose these models. After training, we saw that most of them have had a similar time for training, but not the NASNet, because it's a model very complex with a lot of parameters to be trained. It took us almost 18 hours of training. And because this model wouldn't be feasible to put in production, we decided to remove this model during this time. After that, we needed to reduce even more the number of models, so we scored all the models using the accuracy, loss, and F1 score metrics, And after this ranking, we were able to see that the DenseNet model with 201 layers, the Inception ResNet v2, the MobileNet, and the NASNet model were the ones that had the best results. So the remaining models we decided to not use after this step. So having these 4 models, we increased the size of our data set even more by applying the data augmentation technique. That is, you have one input image, you apply some transformation, and you create virtual examples based on the real ones. So with this data augmentation technique, we obtained more than 250,000 images, and we trained all these models once again. As a result, we saw that almost all the models increased the quality of the results, but not the DenseNet model. So we remove it from the models. And because we saw that the MobileNet and the Inception ResNet models were the ones that had the best results, we chose them to make a final analysis. In this final analysis, we compared across the different classes how the metric F1 score was. But we saw that both models had quite similar results across the different classes. So after that, we made another analysis, but comparing the resources needed for each one of the models. And because of the Inception ResNet model is more than 10 times bigger than the MobileNet, all the metrics that we evaluated here, we can see that the MobileNet had a best result. So that's why we choose the MobileNet as a default model for our solution, even it's being 10 times having 10 times less parameters than the Inception ResNet. Okay, so this is the pipeline that we had before, and now we added the cell classification. But there was still some space for improvement. And the way that we could improve even more this result would be working on the data set. If you see this image, this heat map represents the regions where the beekeeper made more annotations. And you can see that most of the annotations were made on the upper left side of the frame. And this correlates a lot with the regions that we had more wrong predictions. That was on the bottom side of the frame, and in this region on the right side. It's easier to see when you look to the annotations by class, where, for example, here the capped class had more annotations on the center, but had more wrong predictions on the borders. So our hypothesis that what happened was that the model learned to make better predictions because of the beekeeper biases. It learned to better predict cells on the upper left region. And as you can see here, each one represents one corner of the frame. And because of the lens distortion, each one of them shows a bit different the inside content. And probably this was the problem that the model faced, and it was very specialized to detect this kind of cells. So maybe one way to improve these results would be to make more annotation, more evenly distributed across the comb region. Another improvement that we could do, we believe that probably it's possible to have just one neural network, and as input we have one image like this, and the same way that we made the segmentation of the frame, maybe we could make the segmentation of each one of the classes and have as an output one image like this. We didn't try it yet, but maybe it's possible to do. About the performance of this model, we compared the accuracies top 1, 2, and 3. And it's interesting for us to use the accuracy top 1, for example, because we have some weird cells. For example, this one, when we have pollen and an egg in the same cell. We also have here one cell transitioning from the egg phase to the larva phase. So because of these weird things that can happen on the cells, it's interesting to validate also the accuracy of the top 2 guesses that the model have. And we saw that using the accuracy top 2, the performance, the quality improved more than 5%. Okay, about the time performance, we can see in this distribution graph that the comb segmentation, that is that segmentation phase to make segmentation of the comb, have almost the same time, distribution time, of the time to load the image. So it's very fast to use this kind of model for the segmentation. The second method that takes more time is the cells detection, around 3 seconds per image. And the part of the method that takes more time is the classification, because we have more than 3,000 cells to be classified. So because of that, it costs more or less 5 seconds per image. So the entire model, it takes around 9 seconds to process one image using our hardware. We can discuss this later. And also we created, after developing all this solution, we created a final product for the beekeepers, where they can, it's called DeepBee, where they can make the detection, classification, counting automatically. They also can select some regions that maybe they want to work. They also can change the labels of the cells. Maybe the model made some mistake. And after that, the beekeeper can retrain the model based on the correction that he made. And after all this process, the beekeeper can export this result for an Excel file as they used to work nowadays. Okay, about this software we developed, we will make it available open source. It will be in this link, probably in some months, because we have some things to do yet. But we will distribute the data set and the source code that we develop. The next steps, we believe that it's possible to create an API to offer the solution as a service for the beekeepers, because most of them don't have GPUs to process, and also they do this test sometimes once in a year, once in a month. So it's not interesting for them to invest in hardware. Also, we can develop a mobile application, even though it's hard to classify all the cells on an image taken from a smartphone camera. It's possible to reduce this problem and maybe work with just a few classes and make it possible to work on a mobile application. And also, we believe that it's possible to track the development across different images that were taken in some space of time. So you take some images and you can track the development of each individual cells during time. Okay, some takeaways?
Yeah,
Okay.
I can try to.
Yeah.
Maybe it's well known for everybody, but we also want to highlight that not always a big architecture will solve every single issue. So sometimes a more simple model or strategy can give you better results, or at least good enough results. In our case, it was pretty clear that a really small network compared to the big ones have more or less the same results. So for us, it was okay. And the second topic is like this thing that we always say to each other: garbage in, garbage out is really important. If you don't take care of your data sets, don't make the proper cleaning of those things, you might have not so good results. For example, if you don't look into these areas on the illumination of the image or the bias from the labeling process, we might be reinforcing this bias in our models. So we have to do some proper analysis in the data set to prepare it correctly. But I think from my perspective, most important is that we as machine learning engineers, data scientists, and are just enthusiasts, we should also look at opportunities out of this normal track, only finances and or insurance, all those things, because we see a lot of those problems being solved with machine learning, but there are much more around agriculture, or this is a really example where some colleagues said, hey, what's that, man? What are you doing with machine learning in bees? So we really like this kind of projects, and I think there's a lot of opportunity out there for us to apply machine learning and bring up some nice results.
Okay.
That's what we have to present to you, so thank you for listening, and if you have any questions, please shout to him.
Any question? Right?
When we make the cell detection, is that the area with the honey is very challenging to segment?
Yes.
It was even not visible on the picture.
Yes.
Did you also try, but it was normally connected.
Yes.
Did you also try to segment this before, classify this part as honey, and then do the segmentation of the cells for the rest?
No, because the detection were able to put some cells over that area and more or less correspond as the same number of the cells that would have if we could see the cells edges. So that's why we didn't do it. Yeah, but it's also possible to make the segmentation. Yes.
Could you talk a bit more about the decision to go for a sort of multi-phase mono-phase pipeline with preparation, segmentation, classification, rather than use something like faster RCN or something like that for detection and classification in one go?
For recording, your question is about why we are trying to use the RCNN or make some segmentation instead of using the pipeline itself, correct?
Yeah, so my question is, you made it in different, there's different parts, a lot of different decisions,
Yes.
different sizes of filters, and bilateral, for instance, a lot of routers, whereas, there is an approach where you can detect and classify in one go with quite a few different architectures, faster RCN,
Yes.
example, it makes sense, for sure.
Yes.
Could you talk a bit more about the decision making?
Well, we didn't try it yet. Maybe it will work, maybe not. But our idea was that this solution would be faster because it takes some time to make the detection of the cells, and it would be more simple to understand all the solution, and probably it would be faster. But we didn't try it. We don't know if it would really give us good results. Yes.
What type of losses did you use for your classification?
Sorry?
What type of loss did you use for your training?
What type of loss we used? It was a cross entropy.
Okay. No more questions? Well, even if you have more questions, we will be around anyway. We can discuss more gory details. And if you want to have fun with the code later on, it's already on GitHub, so you can check, put some contribution there so we make the project even better. Thank you once again. Hope to see you around.